Hey guys, my name is Hiraku Murakami. I'm here with NovaEdge Academics, and today we'll be continuing with B5 Part 2 of Current and Circuits. So, last time we've talked about, current, voltage, and resistance, etc. Now we're going to talk about how circuits are built and the types of them. Okay, so the first we have series versus parallel. So you have two types of circuit. We have series circuit, and parallel circuit. Now you will encounter a mix of them where you have series and parallel, but this is just to distinguish between the two and see how the calculations are made based off of this. Okay, so first we're going to talk about current and how they're calculated. Okay, so let's say I have a series circuit. In a series circuit, it's actually quite simple. So remember that current is just quantifying the flow of electron with time. How much electron is traveling per second, or actually it's how much coulomb per second, but coulomb is directly proportional to how many electrons. So it's the flow of electron per second, quantifying that. So that means that the current that goes through this, and the current that goes through this, and the current that goes through this, they're actually equal to each other. They're equal to each other, and the reason why is because, let's say you work for Amazon, for example, where it delivers your packages. First, you have the packaging center, right, where they pack your product and they send it to you. So what happens, maybe first you start with boxing, and then you have labeling, and then you have actually, sealing, right? You seal everything and you pack it and send it, right? Ideally, all of these three are happening at the same rate, right? Let's say 1 box per second, 1 box per second, 1 box per second. And that flow is consistent among these three. And that's when you have the most efficiency, right? And it's actually the same way with flow of electrons. So you're going to have the same flow of electron per second, same flow of electron per second, and same flow of electron per second in series circuit. So remember, current is the same in series. Okay, so the I total, or the current overall, is equal to I1, which is equal to I2, which is equal to I3. Okay, so now let's talk about parallel circuit. How does that differ in parallel circuit? Well, here's the thing. You have a number of electrons that are traveling, right? Let's say you have 5 electrons per second. Okay, well, electron can't be in 2 places at the same time. So it's going to split at this junction. So maybe, 4 of them get to here and 1 get to here. And then from this 4, maybe 2 of them get to here and 2 of them get to here, which means you're going to actually have different amount of charge flowing per second in these 3. So I1, I2, and I3, they can be completely different. Okay, so the I total in this case is equal to I1 plus I2 plus I3. 5 is equal to 1 plus 2 plus 2, right? So it's the I total is equal to the sum of them. That's in current case in parallel circuit. Why am I saying this? Because it's actually the complete opposite when we talk about voltage or potential difference. So in potential difference, actually, V1, V2, V3, V total, which is, the battery, the potential difference that the battery has, is equal to V1 plus V2 plus V3, complete opposite. Okay, but in parallel, it's actually the same. So V1, V2, and V3, and V total. This time V total is equal to V1 is equal to V2 is equal to V3. Okay, and let me make an analogy for you for this to make sense, because you need to remember either one, and then you can remember, okay, I can just flip it, right? So let me give a perfect analogy for you. So in series, imagine you're at the mountaintop. You're at the mountaintop. Okay, in series, you actually have 3 humps. Okay, so that's, you have 3 kind of pathways, okay? 3, 1, 2, and 3. So that's V1, V2, and V3. I'm going through them in series, right? I'm going through them back to back to back, okay? And so the potential difference, always remember, it's synonymous to gravity, right? So I have V1 going, V2 going, V3. And the total of this potential difference is V total. Because remember, it's potential difference. It's the difference between 2 points. So difference between 2 points, here it's V1, here it's V2, here's V3. Right? It's the addition of these. And they don't necessarily have to be the same. They can be completely different. And the addition of this is V total. How about parallel circuit? Well, parallel circuit, you have a mountain. I'm essentially going down in 3 different ways that I want. Okay, so I can go down this way, I can go down this way, and I can go down this way, right? Whatever pathway I take, the potential difference is the same. So V total is equal to V1, which is equal to V2, which is equal to V3. Either way, the pathway is the same. So the potential difference between these two and these two, potential difference between these two and these two, and potential difference between these two and these two, they're the same. So V total is equal to V1, which is equal to V2, which is equal to V3. Okay, that's the analogy at least that I use. Okay, and I hope that kind of sticks with you. You might ask, okay, what about resistance? Okay, resistance, it's a bit different from the other two. In the sense that, okay, this one is quite simple. You just add the resistance of the 3 resistors. Okay, but in parallel, you actually have to follow this weird formula. Okay, and we're going to do a lot of practice problems to do this. And this is actually quite important. The ability to calculate the total resistance of a circuit is quite important. You're always going to be doing that as the first step in solving any circuitry problems. And you're going to see it in a second. So let's do a practice problem. So pause the video and give this a try. I'm going to walk you through this. Maybe you just take a look at what I do and then you can try the next problem. I have another one as well. Okay, so first, they tell you to actually determine the total resistance. And the reason why is because they don't usually give us any information on the current. See, they don't even write the total current. They don't even write the current going through this, going through this, going through this, right? So you actually don't start with current, you actually start with resistance. Usually, they give you the potential difference of the battery and the individual resistors' resistances, okay? So let's try to find the total resistance of the circuit. Now, is this first a series or a parallel circuit? It's actually a mix of both. You have a parallel portion and then you have the series portion right here. Okay, so let me try to find the total resistance by simplifying it step by step. So first, I'm actually going to find the resistance, the total resistance of here. Essentially, what I'm trying to do is I'm trying to change it to this because if I make it in series, it's really easy. So this is a mix of 2 ohms and 3 ohms. This is a 1.8 ohm and this is 6 volts. So how do I combine this? By using this formula. So let me call this R1, R2, R3. And this is R1.5. Okay, it's a mix of the two. So R1.5 is equal to 1 over R1 plus 1 over R2 inverse. So that's going to be equal to 1 over 2 plus 1 over 3 inverse, which is actually just 5 over 6 inverse, so 6 over 5, which is actually just 1.2 ohms. Okay, perfect. So I know this is 1.2 ohms. Now I can just calculate the total because I'm just adding these two up. So R total is equal to 1.2 plus 1.8, which is 3 ohms. So that's the strategy that you should be following, which is trying to simplify and parallel, like combine them to make a series circuit. Okay, you're gonna see another problem and you can give this a try. So R total is 3 ohms. Hence, calculate, this is part A, hence calculate the current and power dissipated in each of the resistors. Ignore power for now, we're gonna be covering that in the next video. But let's calculate the current going through at each point. So first, is the voltage known across all of these guys? Do I know V1, V2, and V3? No, I don't. I only know V total, which really sucks, right? So how do I do this? Well, if I know V total, I can actually find the total current because I total is equal to V total over R total. That's following Ohm's law, okay? So that's going to be equal to 6.0 divided by 3.0, 2 amps. So now I know the total current, okay? Now, would you say that this is in series with these two? They are in series to each other. I know these two are in parallel, but this and this is in series, right? Which means the current going through this guy is actually the same as the current total. So I3 is equal to I total, right? So that means that's equal to 2 amps, okay? Now I know I3. So I know I3, R3. I can actually calculate V3. V3 is I3 times R3. That's just 2 times 1.8. So that's equal to 3.6 volts. So the voltage across this resistor is 3.6 volts. I hope you're following with this. If you're not, just replay this portion and see if it makes sense, okay? So I actually know V3 is equal to I3 times R3, which is 2 times 1.8, 3.6 volts. Okay, now I know this, I can actually find the voltage across this. So let me call that V1.5. V1.5 is 6 minus 3.6, 2.4 volts. All right, so now we're dealing with this parallel circuit part. A little bit tricky, but if you remember, in parallel circuit, voltage is the same, right? So V1, let me write this top here, is equal to V2 because they are in parallel. Remember, potential difference across parallel resistors are the same. So they're both going to have 2.4 volts. So V1 is 2.4, which is also V2. So now I know V1, I know R1, I know V2 and R2. So I can find the current in 1 and 2. So I1 is equal to V1 over R1, which is 2.4 volts divided by 2.0. So 1.2, sorry. And I2, I do the same thing. V2 over R2, which is 2.4 divided by 3. Okay, so that's the answer. So now I have the current flowing through resistor 1, current going through resistor 2, current going through resistor 3. Okay, so I know it's a bit confusing. It's really difficult the first time you try it. Try to rewatch this portion of the video and see if it makes sense. I'm also going to do another practice problem to see if it makes sense for you, okay? So let's try this textbook problem. So pause the video and give this a try. Alright, so this one is actually a bit simpler. So I just have two resistors connected in series. So calculate their combined resistance. So first let me draw it. So 5,000, 8,000. Okay, and it's connected to a certain battery. I'm actually not given the voltage. I'm actually given in part B, so I'm just going to write it here. So calculate the combined resistance. So can you notice that they always tell you to calculate the total resistance first? That's always the first step, okay? If you're ever confused, first figure that out. And the reason why they figured that out is because usually the battery is given, so you can find the total current. That's the first step, okay? So calculate their combined resistance. Well, they're in series, so I can just add them together, right? So that's just going to be all right. Part B, what is the current through each of them if they are connected to a 4.5 volts battery? So notice how I don't know the current between each of them. Well, I know R total, so I can find I total. So I total is equal to V total over R total. Okay, and that comes out to 3.46 times 10 to the power of negative 4 amps. Okay, but I'm not interested in the I total. I'm interested in I1 and I2. So let me call this I1 and I2. Okay, but notice how they're in series. So I1 and I2 are equal, and they are equal to the I total as well. Okay, so I figured that out. All right, so part C, what is the potential difference across the 5,000 ohm resistor? So let me call this 1, right? So V1 is equal to I1 times R1. So current is this, and times that by resistance, and I get 1.73 volts. Okay, and repeat these three calculations for the same resistors in parallel with each other. Okay, so I'm gonna erase this and let's try that in parallel. Okay, this is 5,000 ohms, 8,000 ohms. Okay, so let's do the same thing. Calculate their combined resistance. That's just this, right? So let's put that in the calculator. 3,076.9 ohms. Okay. Now, what's the reason why we always calculate R total? Is because I want to figure out I total. So let's figure out I total. 0.0015 amps. That's quite low actually, right? And then now I do each of them. So now, because they're in parallel, the current going through this is different from this, okay? And just a rule of thumb to always remember, if the resistance is lower, it's always going to have higher current, okay? And the reason why is because electrons tend to go through the easiest pathway, okay? You're also going to see this through calculation of this being validated. So another piece of information we know is that V total is 4.5. And we know in parallel, V1 is equal to V2. And it's equal to 4.5, right? So if I know V1 and R1, can I find I1? Yes, I can. So I1 is equal to V1 over R1. 9 times 10 to the power of negative 4 amps. And I2, which is V2 over R2. Boom. Okay. And now let's find the potential difference across 5,000 ohm resistor. Well, we actually already know that to be 4.5 volts. So 4.5 volts. Okay, that's it. All right. I hope this was clear. Actually, this problem was way easier than the previous one. So if you want to challenge, try again the previous problem and see if it makes sense for you. All right. So now we're going to talk about ammeter. Okay, ammeter, just a device that measures current. So device that measures current. Right? Because we're doing this in calculation, but in reality you need a device to actually measure it, right? We can always calculate the theoretical, but right? And one thing you need to know is there's something called ideal ammeter, and the ideal ammeter has no resistance. Okay, so these ammeter, the best case scenario for an ammeter is to have no resistance, and you always plug in ammeter in series. Okay, so maybe I put an ammeter here. Okay, and the reason why I put an ammeter here is because the current that it's going to experience here is going to be the same as it experiences here as well. Okay, so if I want to figure out the current going through here, I put it in series with it. If I want to figure out the current going through here, I put an ammeter here. If I want to figure out current going through here, I put ammeter here. And the reason why is because they're going to be in series, so the current experienced through here and here are exactly the same. And that's how you can measure the current. Right? So why does it have no resistance? Well, because remember, if it has a resistance, then it's going to totally change R total, right? Because, well, R total is a function of resistance of this plus this plus this plus this. Okay, if I put it here, then it's going to be this plus this plus this plus this, right? Either way, like addition of either you do it to parallel or series, it doesn't matter. It's going to change the R total value. What does that do? Well, if R total changes, then I total changes. If I total changes, then you're completely screwing up the circuit that you're trying to measure the current of, right? So if plugging in the ammeter screws up the total current going through the system, then that's no point. So ammeter has no resistance whatsoever if it's ideal. They are going to ask you in paper 2 for sure about either ideal ammeter or ideal voltmeter or both. So we're going to touch voltmeter next. Okay, so voltmeter is the device to measure the voltage or the potential difference. Okay, and this one you want to put it in parallel. Why? Because in parallel voltage is the same, right? So if I want to measure the voltage of this guy, let's call this V1. I'm actually going to put it in parallel a voltmeter like this, because guess what? Voltmeter is also going to experience V1 as well. Okay, and interestingly enough, this also comes into play about the fact that potential difference, you're trying to measure the potential difference between 2 points. So you're measuring actually the potential difference between 2 points across the resistor. So conceptually speaking as well, this completely makes sense that you take one point A, point B, and seeing how much potential difference there is in that system. Okay, you're actually measuring something called the potential drop across the resistor. Okay, so that's how a voltmeter works. So if I want to measure the voltage of this guy, I'm actually going to put it in parallel with this guy. Now, notice how if I put this like this, it's also the same thing as putting it in parallel with this guy as well, because, well, now it looks like parallel between 3 resistors, right? So putting it in parallel with this will also measure the voltage of this guy, and it makes sense. Voltage across this, both the same thing, right? Now, in the ideal voltmeter case, it actually has infinite resistance. Why? Because we don't want it to be experiencing current going through it. So we want the current to go through this guy only, okay, with like tiny bit going through this way, okay, only that, okay. And the reason why is because, well, if you know, I have like a current going through here and half of it goes here and half of it goes here, well, remember that V1 is equal to I1 times R1, right? So if I reduce the current going through here, what's going to happen? It's going to screw up the voltage that you're trying to measure, right? So if you don't want to screw up the voltage that you're trying to measure, then current has to be constant. R1, of course, is constant. So you don't want to change the current. So if I'm plugging it in like this in parallel, I need it to have infinite resistance in order to not change the current going through here. Okay, does that make sense? All right, so that's the concept behind voltmeter and ideal voltmeter. So summary, ideal ammeter has no resistance whatsoever. Ideal voltmeter has infinite resistance. Okay, remember these two conditions and also be able to explain why in your exam. All right, we're gonna stop here. Next video, we're gonna cover EMF and power, electrical power, as well as a few other advanced stuff. Okay, so if you want to check that out, then check that out. I'll see you in the next video. Hey guys, thanks for watching. If you like this kind of video, then consider giving us a like and subscribing to our channel. We have a lot more lecture style video and content like this in our channel, so feel free to go check it out. If you're looking for additional guidances like one-on-one tutors in IB subjects, SAT, TOK, essay, IAs, writing, etc., then go to our website at NovaEdgeAcademics.com, fill out the form, and we'll get in touch with us. In the meantime, we'll see you in the next video.